So for exercise 2, what we're looking at is this Appalachian Regional Commission data set of the counties. You can get off of the eCampus site. And we're going to investigate if these water resource characteristics in this particular region are clustered, random, or dispersed using this get-stored statistic. And we're using this get-stored statistic specifically for some attributes for these counties. And we can't use the average nearest neighbor because it didn't allow us to test for the attributes. So this is a global statistic in which we're going to get one value, one reported value for the whole entire study area. So I'm going to go in now and I'm going to add in the data that I've already unzipped from the eCampus site, ARC Counties Water Summary. So you download the file, unzip it. I unzipped it to my ctemp RESM 540 work folder, and now I'm adding it to my display. So I didn't have anything else added in there, and a good thing to do is to check to make sure that your data is in a projected format, as I mentioned in the lecture part. So I'm going to right click and say Properties, Source, and you can see under the spatial reference that this is USA Contiguous Albers Equal Area Conic USGS projection with the information you see there. So that's a good thing. The other thing you might want to do, well, you can see the state boundaries in the background pretty well with this, but it's always really good to investigate the different attributes of your data set that you plan to look for these spatial statistics questions on. So what I'm doing now is I'm just looking at the attribute table to see all these different fields across the top, and I can access the README file for this topic to get more information about these. And essentially what I'm going to be looking at is this normalized groundwater score, which is assigned to each one of the counties. And I am going to look at this normalized, GW normalized NRM field, and just doing some general sorting top to bottom, low to high, and so on. I'm investigating this field in a little bit more detail. And so the higher the value for this particular attribute called groundwater normalized, the higher the value, the better the groundwater aquifer and the wells are in that particular county. So we're looking for essentially asking the question, testing the hypothesis, is do good groundwater resources occur near each other throughout this region, or are they scattered with no real pattern? And the reason why we might want to know that is because if there is a good cluster of good groundwater resources, maybe we should protect those. Maybe those should have different things occurring on the landscape to protect that groundwater resource better in terms of how we treat our water systems, how we look at infiltration, how we look at different watersheds and streams and rivers in those areas. All are part of and can contribute to our groundwater resource. So to look at this groundwater value in more detail, besides just looking at the aspatial values in a table, we can also come over here, and this is always a really good idea, just to get an understanding visually of what's going on with your data, is to do like a graduated color display. So I'm going to look at this groundwater resources, the GW normalized field, and I'm going to choose a different color for this, something like that. Turn these on, and that doesn't really break it up too good. Let me try a different color for this. Not too jazzed about that one, so let's try something that's maybe a little bit easier on the distribution. Let's just try this yellow to green, something like that. Okay, that's a little bit better. So what this is telling me is some of these really high scores, this darkest green, you can see them kind of, looks like there's a pretty good cluster here in the central part of West Virginia, especially over here in Kentucky as well. And then Pennsylvania, there's a little group right here. So visually I see some clustering, so I would kind of expect my spatial statistics to tell me that the high values do seem like they're clustered. for this groundwater resource, which would help identify a pretty large areas that we see for different policies. Okay, so what we're going to do is run some spatial statistics for this to try to answer that question. Are all the values for the groundwater scores clustered or not on high or low values? So we're going to this high-low clustering, and my input feature, my counties, input field, I'm going to choose that groundwater normalized. My conceptualization of spatial relationship. This is where, when we talked about in lectures, we're going to use this specific one, which is the, oops, sorry, don't mean to do that, zone of indifference. Okay, so my zone of indifference is the conceptualization of spatial relationship. That's the one that has some characteristics of both a fixed distance span and also the inverse distance span. Row standardization, I'm going to choose this because I'm using polygons. And I want to put a value in here. I want to choose a distance band threshold distance because if you remember from the lecture, go to that for a second, this is what I'm after. I want to find out what distance to use as part of this zone of indifference. So that distance band or threshold distance would go in here. But I don't know what that distance is that's important for it to search and look in terms of the relationships of those polygon centroids to the ones near it. So we're going to let the data tell us at what particular distance we see spatial autocorrelation occurring. Spatial autocorrelating, or autocorrelation, meaning that things that are closer are going to be more related than things farther apart. So I'm just going to put this on the shelf over here for a second. I'm going to go to my tools again, and I'm going to go now down to incremental spatial autocorrelation. So now my input is the counties, input field, that same groundwater normalized score. Distance bands, I'm going to keep this at 10 for this one because I've got a lot of locations here. I think 10 will give me a pretty good graph of observations, and that's fine. I'm going to keep this open for my beginning distance and increment. My distance method is Euclidean. Row standardize, again, is checked because I have polygons. And this is where I'm going to put an output table or an output report file. I'm not going to worry about the output table because I can show you where the values that I need are in the output report. So I'm just going to specify an output report file. I'm going to call this, I'm going to go to my C temp in my RESM 540 folder that I'm doing work in, and I'm just going to specify incremental spatial autocorrelation, so I'll call it ISA for groundwater. I think it was normalized like that. Okay. Click save. Whoops. I'm going to make this a PDF file. Oh, okay, it's automatically put that PDF on there, which is good. Now, when I'm going to say run, what's going to happen is it's going to find that value, as you can see here, in which spatial autocorrelation occurs. Okay? So, when I say view details, I can look at the output from this, and you can see my output report file is right here, this PDF. So I'm going to click on this. When I click on that, my PDF viewer comes up, and oops, it looks like this. So spatial autocorrelation by distance, z-score, that's the significance. Now with 10 distance bands, I have 1, 2, 3, 4, I have these 10 points. If I wanted to crank that up, I could use 15. If I didn't feel like this was too had too many steps in it, I could increase the number of distance bands to make this a little bit more precise. But as you can see, this is significance. And the z-score, any of the ones that are darkest red here, these are significant. As you can see, greater than the 0.258, which is greater than 99% confidence interval value. And what we're interested in this is the first peak. So the first peak is here, and that corresponds to a distance, which is kind of hard to see. So this is the distance I want to use and input into my other command over there. Whoops. Just got spun around there. This distance is what I want to find. So it's hard to get that distance off of this graph. So we're not going to use this graph, but we want to find essentially that first peak, which should be around here something. Looks like 145,000, something like that. But I can get that value if I come over here to my output and I look at that first peak. That's it right there, that 143. So I'm going to highlight this. I just clicked on it. I'm going to say copy. I'm going to use that value now in my other command, which is the get a sword statistic. So I can put that value right in here by saying paste, and that's what I want to use for those counties and that specific field. So this would be different. I'd have a different incremental spatial autocorrelation value if I use a different field, which is what you're going to do in the lab exercise. But for the first one, we're using this groundwater normalized. We're going to generate a report. We're going to use the zone of indifference, and we found this value of 143,363. That's essentially the distance right in here for this, where that first peak of the incremental spatial autocorrelation identified for this. And now we're going to run this. And again, we're going to have an output report, which is going to be created. Okay, so my report file is down here. Let me move this over. And if I go to view details, you can see in my details that I've got this output file, which is an HTML file. So my report for this question of this hypothesis test is found in this HTML output. So again, my null hypothesis is that there's a random pattern, there's no clustering of the high or low values, and I'm testing that. And when I click on my HTML report file, an HTML browser pops up. This is the file. And as you can see, given that z-score of 4.7, there is less than a 1% likelihood that this high clustered pattern could be the result of random chance. So that means I can conclude that the values for these ARC counties based upon the groundwater normalized score are clustered. We have clusters of the high normalized groundwater scores. Okay, so what we saw visually, we just verified statistically with this get a sword global statistic.